In this video, we're going to look at linear approximations and differentials. We are going to describe what a linear approximation to a function at a point is. We're going to write the linearization of a given function. We're going to draw a graph that illustrates the use of differentials to approximate a change in quantity. And then we're going to calculate the relative and percentage error using a differential approximation. So we're going to use derivatives and equations of tangent lines to evaluate our function close to a known quantity for a derivative or a known output. So like the square root of 2 or the square root of 4.1 or something like that. So we'll start with something simple, and f of x is equal to 1 over x. So the first thing we do is we find the equation of the tangent line. So f prime of x is equal to negative 1 over x squared. And say I would like to find the value of what f of 2.1 is. To do that, I would find a value of a known quantity, which is 2, right? So f of 2 is 1/2, or in other words, 0.5. f prime of 2 is negative 1/4. And so we get the equation of the tangent line, which is right here. We can use this equation of a tangent line to approximate the value of f of 2.1. So I put in to this equation of a tangent line, I put in the value that I'm really interested in, which is 2.1. I put in 2.1, and so the difference between 2.1 and 2 is 0.1. And so I have 1/2 minus 1/4 times 0.1, and that'll give me an approximate value as if I were to put in 2.1 into the original function. And you're probably asking yourself, why don't I just put it in the original function and use my calculator? Well, back in the day, we didn't have calculators. Somebody had to figure out what this would be. And one of the ways that we found square root tables, cosine tables, sine tables was one of the ways was with linear approximations back in the day before calculators. So suppose f is differentiable on an interval I, doesn't even say open, on an interval I contained in a point A. The linear approximation to f at this A is my input value at A, and then f prime of A, and then x minus A. This is the equation of the tangent line. So this is what we just did. My f of A was 2, and we know that was 1/2. My f prime of A, which was 2, in this case was negative 1/4. And then I had x, which in this case would have been 2.1 minus my A, which was 2. So we can approximate the value of 2.1 if we didn't have a calculator using a linear approximation. So if we want to find the linear approximation at x is equal to 1.1, so I want to do the square root of 1.1 without a calculator, I can do the linear approximation. So I know I'm going to use f prime of A, and I need that. I need x minus A, and then I need f of A. Now, the only reason I'm doing this slightly different than what I just said it was from up above is because this is the m x minus x naught plus y naught kind of form. So I'll need to know what f prime of x is. So f prime of x is going to be 1/2 x raised to the negative 1/2. I need to evaluate f prime at 1 because that's the closest to 1.1 that I know the value of. And so this is going to be 1/2 multiplied by 1 over the square root of 1, which is just 1/2. So now I have my f prime of 1, I have my A, which is 1. My x in this case is the 1.1 because that's what I'm really trying to evaluate it at. The only thing I'm missing is my output, so I also need my f of A, so f of 1, which is equal to 1. My linear approximation then is equal to my f prime, which is 1/2. I'm going to use this form. F prime of A is 1/2. My x is 1.1, because that's what I really want to evaluate it at. I'm going to subtract off 1, because that is the point I am looking at, my known quantity. And then I'm going to add to it my output, my y naught, which is 1. So what I really have, this is the square root of 1.1 is approximately equal to 1/2 multiplied by 0.1 plus 1. And you're like, well, don't I still need a calculator? Well, not really, because I have 1/2, and 0.1 is the same thing as 1 divided by 10 plus 1. So this really is 1 over 20 plus 1. And so this is 21 over 20. And that's approximately what 1.1 is, the square root of it. So we can tell you approximately the square root of 1.1 is about 21 over 20. So the first thing we want to do when we're asked to do an evaluation is we're going to use the fact that we'll need the 3 pieces. We'll need f prime of a, which is the slope of the tangent. I'll need f of a, which is my y naught. My a is the x naught, and then x is the point we really want. This is our want point, or a want input. Those are the things that we need. So if I'm asked to do a here, I'm asked to find the linear approximation at 0.75. Well, 0.75 is close to pi over 4. If I were to put pi over 4 in my calculator, it's like 0.72 or something like that. So what I'm going to need is I'm going to need f prime of x, and this is going to be the cosine of x. I'm going to need f prime evaluated at pi over 4, because this is my slope. Remember, this is my slope, so it's going to be the cosine of pi over 4, which is equal to the square root of 2 over 2. This is my slope. I will need my x naught. Well, my x naught is pi over 4. My y naught is going to be equal to f of the pi over 4, which is the sine of pi over 4, which is the square root of 2 over 2. So f of 0.75, which is equal to the sine of 0.75, is approximately equal to my slope, which is the square root of 2 over 2, multiplied by my point of interest was 0.075 minus pi over 4, and then plus my output, my y naught, which was the square root of 2 over 2. Now, yes, to actually get a decimal equivalent, that would be needed to use a calculator, because I need to know the square root of 2. Or actually, if I'm like, really, I have nothing better to do on a Friday night, I can find the approximation of the square root of 2 over 2 and the approximation of pi over 4 and do this hand calculation. Am I going to ask you to do that? No, I'm not going to ask you to do that. Now, the other thing it's asking me to do, which I will need a calculator for, is to compute the percentage of error in your approximation. The percentage of error is 100% multiplied by the approximate minus the exact, and then the absolute value of that, so make sure it's not negative, divided by the exact. So I will need my calculator to find the percentage of error. So I got my calculator out, and this value here, this value, I'm going to go out to 4 decimal places, is equal to 0.6821. Now I'm going to get my calculator out, and I'm also going to figure out what f of 0.05 is using my calculator, making sure I am in radians. And this will be the exact to 4 decimal places. And to 4 decimal places, I got 0.6816. Now I'd like to know what my percentage of error is. So my percentage of error is going to be 100 times. So I'm going to do 100. Oh, I don't know what that was all about. Let me erase that. I was using the highlighter instead of my pen. So it's going to be 100 times the absolute value of the approximate, which is 0.6821, minus the exact to 4 decimal places, which is 0.06816. Absolute value of that whole thing divided by the absolute value of the exact, which is 0.6816. So I'm going to get my calculator out. I'm going to plug that in, 100, and then times 0.6821 minus 0.6816. I'm going to divide that by 0.6816, make sure that nothing's negative. Multiply that baby by 100, and I end up, even after multiplying by 100, I've got 0.073%. So my margin of error is actually, my percentage of error is actually pretty darn close to, that tells me I'm pretty darn close with my approximation than if I would have just put that in my calculator. So that's actually kind of nice. Okay, so I'm going to go ahead and do the second one. I'm going to set it up. I'm going to set up the third one as well, and I want you to practice the percentage of error. So I'm going to come over here, and I'm going to find, for B, I need the f prime of x. Now this is either the quotient rule or the chain rule. I'm going to use the quotient rule this time, so it's a derivative of the numerator, which is 1, multiplied by the denominator, which is x plus 1, minus the derivative of the denominator, which is 1 multiplied by x, all divided by the denominator squared. And so I'm just going to clean this up a little bit because I'm going to do the plug-in. So I have x minus x, so I have 1 over, and I have x plus 1, the quantity squared. I need to know what that is evaluated at 1. So I'm going to put in 1 over 1 plus 1, the quantity squared, which is 1 over 2 squared, which is 4. So this is the slope of my tangent line. I need to know what f of 1 is. This is my y naught, so I have 1 over 1 plus 1. So I have 1/2. This is my y naught. So my linear approximation, so f of 1.1 is approximately equal to the slope of my tangent line evaluated at the 1, which is 1/4. My x is 1.1 minus my a value, my known value is 1. And then I have the plus my y naught, which is 1/2. And so that is approximately equal to what 1.1 is if I were to put that into this x over x plus 1. Again, to find compute the percentage of error, it's 100, the approximate, this number, whatever it is, minus the exact. The exact is found by putting 1.1 into this original function, absolute value of that, and then divide by the exact. And for my percentage of error, my error for mine here ended up being 0.23%. So that's actually a really close linear approximation. Let's do this last one here. There we go. Erase that. When we do this last one, we're going to, of course, need to find my f prime of x. My f prime of x is e to the x. F prime of 0 is e to the 0. This is 1. This is the slope of my tangent line. My f of 0 is e to the 0. This is 1. This is my x naught. That's my y naught. That is my y naught. So now I'm ready to do the linear approximation. So f of 0.05, I'm one too many zeros, 0.05 is approximately equal to my slope, which is 1. I have my x, which is 0.05, minus my a, which is 0, plus my x naught, which is 1. So this is approximately equal to 1 times 0.5, and then, so 1.05. And then, of course, to do the percentage error, you're going to take the approximate minus the exact, divided by the exact, absolute value, all of that, multiply by 100. And my error is 0. My error is 0. One too many zeros. 0.12%. All right. Now, on these next examples, they're not giving me the a, and they're not even telling me what the function is. But I can tell if I'm trying to evaluate the tangent of 3, my function is probably, f of x is probably the tangent. 3 degree tangent of x. 3 degrees is close to 0. It's closer to 0 than it is a known quantity, which is 45 degrees. So I'm going to use the A is equal to 0. And for B, here, I'm going to use my f of x. It looks like what I'm asked to do is the cube root of x. And I know the cube root is 64, which is 4. So I will use A of being 64. And then on C, it looks like C, my function f of x, I would use the square root of x. And then 5 over 29, that looks like it's close to perfect squares. Let's go 4 over another perfect square that's close to 29, because I want to choose something that's close to 29 that's a fraction. So I'm going to use a 4 as a perfect square, maybe 4 over 25. Because the square root of 4 I know and the square root of 5 I know. So starting up with A, you're going to find f prime of x, which is going to be the secant squared of x. F prime evaluated at 0. Secant is the reciprocal buddy of cosine, so that's going to be 1. My f of 0, the tangent of 0 is 0. That's my y. This is my y naught. This is my slope. My A is the same thing as x naught, and my x that I need to put in is 3. So my linear approximation L of x is going to be my slope, which is 1. My x is 3. My x naught was 0. And then plus my y naught, which is 1 for that one. Going through this, we're going to do f prime of x, which is going to be 1/3 x raised to the negative 2/3. F prime evaluated at 64 is going to be 1/3, and I have 1 over the cube root of 64, and then that quantity squared. So this is going to be 1/3. The cube root of 64 is 1/4 squared, gives me 1/16. And this is going to be my slope. F of 64, this is my y naught, is going to be the 3rd root of 64, which is going to be 4. My A is my x naught, and my x is 65. So my linear approximation for this one is going to be my slope, which is 1 times 3 times 16, which is 48. My x is 65 minus my x naught, which is 64. And then plus my y naught, which this is my y naught, which is 4. So that is the linear approximation. And then on C, I'm going to do f prime of x. This is going to be 1/2 x raised to the negative 1/2. I'm going to do f prime evaluated at 4 over 25, which is going to be 1 over 25 multiplied by 1 over the square root of 4 divided by 25, which is the same thing as 1/2 multiplied by the square root of 25 over 4, which is going to be equal to 5 over the square root of 4 is 2, so 2 times 2 is 4, so it's 4/5. This is my y naught. This is my x naught. Or excuse me, that is my slope, not my y naught. That is my slope. So that's my m. My y naught is f evaluated at 4 over 25, which is the square root of 4 over 25, which is 2 over 5. This is my y naught. So L of x is going to be my slope, which is 5/4 multiplied by my x. My x is the 5 over 29 minus my x naught, which is 4 over 25, plus my y naught, which is 2 over 5. And that is my linear approximation. We can vary the linear approximation by using the fact that f is approximately equal to, if we solve for the f prime of ax naught, this is my delta x, and then f of x minus f of a is my delta y. So this is going to start leading us to actually really nicely into later in this when we start doing the integrations. when we do delta x, delta y. So we basically are moving the f of x minus f of a is the delta x, which is what we're familiar with, and the f prime of a multiplied by x minus a, that is my delta x. So suppose f is differentiable on the interval a containing the point, the interval I containing the point a. The change in the value of f between the 2 points a and a plus delta x is approximately equal to delta y is approximately equal to f prime of a multiplied by delta x, where a plus delta x must be in I. So we want to approximate the change in atmospheric pressure when the altitude decreases from 2 to 2.01 when P of z is equal to this. So we are going to use the fact that delta y, because that's what they're really asking for, is this change in the atmospheric pressure, is going to be equal, approximately equal to my f prime of a and then my delta x. Now, these are my inputs, or my delta x, or my, well, give me my delta x. My delta x is, it's going to change from 2 to 2.1, so it is a 0.01 change. That's my delta x. So then all I have to do is find f of a, well, p prime. I'm going to do p prime of z, which is equal to, so it is 1,000 e raised to the negative z over 10, and then multiplied by the derivative of negative z over 10, which is negative 1 over 10. Now I'm going to evaluate this p prime of z. I'm going to evaluate it at my initial input, which was 2. So this is going to be 1,000 e raised to the negative 2 over 1 over 10 multiplied by negative 1 over 10. I'm going to get my calculator out. And so I have 1,000 times e raised to the negative 2 divided by 10. And then that gets multiplied by a negative 1 over 10. So my answer is negative 81.87. So what does this tell me? This tells me as z goes from 2 kilometers to 2.01 kilometers, my pressure is decreasing by 81.87. Oh, wait, stop. I still need to multiply that by delta x, don't I? So my delta y, I got so excited, my delta y is approximately equal to the negative 81.87 multiplied by my delta x, which is 0.01. Don't forget that part. I was just like all Johnny and wanted to be done, I guess. So what this is telling me is that this is approximately changing at that moment from 2 kilometers to 2.01 kilometers of negative, which means it's decreasing, 8.8187. There we go. And then whatever my units would be, whatever my units for pressure is. Okay, so approximately the change in, I guess I like I's there, the volume of a right circular cone with a fixed height of 4 when its radius is increasing from 3 to 3.05. So we know what my delta x is, right? So this is my delta x, which is 0.05. That's the difference between them. And so what I have to do then is I have to find v prime of r. V prime of r is going to be 2 pi r h divided by 3. But h was 4, so I can put that in there. So I can just put that 4 right there. Now I need to evaluate this at 3. So v prime of 3 is going to be equal to, I have 4 times 2, which is 8 pi 3 divided by 3. Those cancel, so I get 8 pi. And so my delta y, my approximate change in the volume here, so my delta y, or the approximate change in my volume, will be my 8 pi multiplied by, don't forget, the 0.05, and then whatever that is. Okay, now we're going to let f be a differentiable, on an oh, I always want to say open because usually it's open, on an interval containing x. A small change in x is denoted as dx. Then we can change the corresponding y is equal to f of x. So we can say dy is f prime of x dx. Again, this is setting us up for later when I wanted to be able to do integrations. Notice that we have delta y ends up becoming f prime of a dx. So we can say dy is equal to f prime of a dx, where dx is that change. Okay. Consider the following functions and express the relationship between the small change in x and the corresponding change in y in the form of dy is equal to f prime of x dx. Okay, now this is nothing new. Basically what we are really doing is saying, hey, let's let this thing equal y, let's do the derivative. So dy dx is equal to the sine of x multiplied by the cosine of x using the chain rule. However, that is not what they want us to do. They want us to say dy equals, so in other words, I could think about this as multiplying dx by both sides. When I do that, I'm going to get dy is equal to the sine of x times the cosine of x, that was a terrible C, multiplied by dx. That's all they're asking us to do here. On B, same kind of thing. So I'm going to do f prime, and I say that as y, so dy dx is equal to, I'm going to use the quotient rule. The derivative of the numerator is 1 multiplied by 4 minus x, minus the derivative of the denominator is negative 1 multiplied by the numerator, which is 4 plus x, divided by the denominator, which is 4 minus x, the quantity squared. I'm going to clean this up a little bit algebraically and say dy dx is equal to, well, let me see, if I distribute this through, that's going to be a positive, so that's going to just be 4 plus x. My x's will cancel, so I'll end up with 4 plus 4, which is 8, over 4 minus x, the quantity squared. Multiply both sides by dx. Think about it as doing it, multiplying both sides by dx. So I've got dy is equal to 8 over 4 minus x squared dx. And that's all they want me to do, which is nothing different than what we have been doing up until this point. Now let's take a look at our last one here. So y is equal to the natural log of 1 minus x. Dy dx is 1 over 1 minus x multiplied by 1 minus x, which is negative 1. So dy is equal to negative 1 over 1 minus x multiplied by dx. And that is my answer. And that's it for this video. So it's not a very long video compared to some of the others, and we will see you in class.